All right, everybody, here we go. This video is going to do two proving identities. That's it, just two of them. They're a little bit more challenging, so I thought it would be nice to have a little video of some of the more challenging examples. This first one we're going to do is not necessarily difficult, it's just longer in steps. So this is a perfect example where the first thing we want to do is get common denominators, because we do have two different fractions here. So our common denominator is going to be cosine x times 1 plus sine x. So obviously this side needs the 1 plus sine x, and this side needs the cosine x. And after we multiply that on the top, we are going to have 1 plus sine x times 1 plus sine x all over cosine x times 1 plus sine x plus cosine x times cosine x all over the same denominator. And of course it's equal to 2 secant x. Now, resist the urge to cancel things, because we just put them there. You can't put them there and then cancel them. So what you want to do now is you want to FOIL the top. So if we FOIL this, we are going to end up with 1 plus 2 sine x plus sine squared x plus, and then we're going to multiply the top here, and we're going to get cosine squared x. Now, of course, since we're adding this, this is all over cosine x times 1 plus sine x. As you are looking at this, I hope you notice that this right here is one of your Pythagorean identities. So sine x, or sine squared x plus cosine squared x, we know is 1, and 1 plus 1 is 2. So this is going to give us 2 plus sine x all over cosine x times 1 plus sine x. And that's going to be equal to our 2 secant x. Now from here, what you're going to want to do is factor out a GCF of 2. So we can factor a 2 out of here. That's going to give us 2 times 1 plus sine x all over cosine x times 1 plus sine x. That's equal to 2 secant x. Yep, these guys right here are going to cancel. That'll leave us with 2 over cosine x is equal to 2 times secant x. And you can see the last step is to just use your reciprocal property and bring the cosine up to the top, and that'll leave you with 2 secant x is equal to 2 secant x. Okay, so that wasn't necessarily a difficult problem. It just involved multiple steps, so I just kind of wanted to show you that one. What we're going to do now is go to a more challenging problem. It's not super long in steps, but it's got a few real clever things you need to do. So we're going to do that one next. So here we go. This one is a little bit different, and we need to get something to happen with that denominator. And one of the tips that you have been told before is you can multiply these by a clever form of 1. So one step that is helpful in these that are kind of difficult to start is to multiply the top and bottom by the conjugate of the denominator. So we're going to multiply the top and bottom by 1 minus cosine theta. And when we do that, the top is going to be FOILed, and you're going to have 1 minus 2 cosine theta plus cosine squared theta all over. And when you FOIL the denominator, that's going to be 1 minus cosine squared theta. Okay, so all we did is multiply the top and bottom by the same thing. That's a clever form of 1. So now you got to look to see what else you can simplify. The denominator has another Pythagorean identity. 1 minus cosine squared theta is sine squared theta. So we're going to have 1 minus 2 cosine theta plus cosine squared theta all over sine squared theta. Now from here, I want to show you another little trick. You are not allowed to do this when you have one term in the numerator, but when you have 3 different pieces or 2 different pieces in the numerator and 1 denominator, you can actually split them. So this is going to be 1 over sine squared theta minus 2 cosine theta over sine squared theta plus cosine squared theta over sine squared theta. Now, we did that for a couple of different reasons, and one of them is to turn 3 pieces into 2 pieces, and I'm going to show you how we do that next. But everything we've done so far is mathematically correct. You are definitely allowed to split the numerator into pieces over the same denominator. You are never allowed to split a top that has 1 piece and a denominator that has multiple pieces, okay? That is not allowed. Don't do it, okay? So after we split that up, sine squared theta in the denominator can just be brought to the top to cosecant squared theta. And when you have 2 cosine thetas on the top and sine squared theta on the bottom, what you can do is think of sine squared in this way. So this is 2 cosine theta over sine theta times sine theta. And we're going to use that in just a second. And then cosine squared over sine squared, cosine over sine we know is cotangent, so cosine squared over sine squared is cotangent squared theta. So I did this for a reason. We know that cosine over sine is cotangent. And we know that sine in the denominator can be brought to the top as cosecant. So this step can now be written as cosecant squared theta minus 2 cotangent theta cosecant theta plus cotangent squared theta. And that, of course, is equal to our usual cotangent minus cosecant squared. So we have just a couple of more steps here. And first thing you need to do is switch the cosecant and cotangent. Because they're both positive, we are allowed to switch those. You can't switch when there's a negative, but you are allowed to switch when it's positive. And the reason we're doing that is because we want cotangent first and cosecant last. So we're just going to switch those two, okay? So we're just going to say that this is cotangent squared theta, and this is cosecant squared theta. Again, you can only do that when they're positive. You can't do that when you have a negative, unless you're going to factor out a -1 or something like that to be slick, but you can't just switch them. Okay, so that's still equal to the line above. Now, all you have here is a factoring step. This is what multiplies to this squared, and this is a minus. This is just going to give you cotangent theta minus cosecant theta times cotangent theta minus cosecant theta. It was just a factoring step, and that's still equal to our cotangent theta minus cosecant theta squared. And since these are the exact same, you guessed it, you're done. Cotangent theta minus cosecant theta squared And we are finished. So the reason I wanted to do this one with you is because of the clever way of multiplying by 1 in the first step, being able to split a numerator that has 3 pieces into 3 separate fractions when it all has one denominator, and being able to switch those guys because they're both positive. Okay, so I wanted to show you a couple of different things here. And also, when you split a sine squared, you can do this just so it helps you see that you have a cotangent and a cosecant. Okay? This was definitely one of the more challenging proofs that we've done. And there we are, 11 minutes for 2 problems. This is Longo and I'm out. See you, bye.